Patty's Calculus videos, written and performed by me, Patty Leitner.
Part 4, Integrals. Section 4.9 and 5.4, Antiderivatives and the Indefinite Integral.
Lesson 1, Antiderivatives and Integrals. In this section, we learn about what are called antiderivatives and the indefinite integral. And this means that we're leaving the first part of calculus, which is usually referred to as differential calculus, which is all about finding the derivative of a function. And now we're going to be entering the second part of calculus, the second half, which is called integral calculus. And that's all about finding the antiderivative of a function. So in the first semester of calculus, we really just get an introduction to integral calculus, and then you'll learn much more about integrals if you go on to second semester calculus. I do want to mention just kind of briefly that finding an antiderivative is sort of the opposite process of finding a derivative, and we'll find that out in just a minute. So it's a little bit like matter and its opposite, which is called antimatter. Okay, let's see how this works. So suppose I tell you the following. Suppose I tell you that some function, I'm going to call it capital F, its derivative, capital F prime of x, is 5x to the fourth. So I'm giving you the derivative of a function, and I want you to think backwards. So here we're going to be thinking backwards and try to come up with a function that would have this 5x to the fourth as its derivative. Can you guess what function f would have to be? It would have to be x to the fifth power in order to take the derivative of this and end up with 5x to the fourth. So I put down here, notice you are thinking backwards. Instead of giving you a function and saying find the derivative using the power rule for derivatives, I'm asking you to start with the derivative and work backwards to find a function whose derivative would end up being this. Oftentimes I compare this to the game show Jeopardy, and if you haven't seen it, it's a game show where they make you think backwards. They give you the answer, and then the contestant has to come up with the corresponding question. So, an example of the type of thing that happens in Jeopardy, they often have different categories. So, for example, they might have a literature category. And the answer to the question would be, most consider King Lear his greatest tragedy. And the contestant would have to come up with the question, and so their answer has to be in the form of a question, and they might say something like, who is Shakespeare? Or here's a sports category, they love to put sports in there. With this record number of Grand Slam titles, Roger Federer is considered by many to be the greatest tennis player of all time. And so you have to come up with the question, which would be, what is 16? He has 16 Grand Slam titles, at least as of the moment that I am producing this video. Here's one in math. It's the number you have to cube in order to get 64. So you're thinking backwards, what number do I have to cube in order to get 64? And so the question you might come up with is, what is 4? But in all of these cases, you're thinking backwards. The Jeopardy people give you the answer and you're coming up with the question. And that's what we're doing when we're finding an antiderivative. Okay, let's go ahead and check our answer down here. We said that if f prime of x equals 5x to the fourth, then f of x must be equal to x to the fifth. That's what we said right here. And what we're going to do is try to see if there's a way to check this answer. Maybe I'll call it a claim. So I claim that the function whose derivative is 5x to the fourth is x to the fifth. And is there a way that I can check that claim? There is. I can go ahead and differentiate. So we can always check by going back and differentiating. So let's go ahead and go in the forwards direction, the direction we're used to, differentiating. So if I want to check this claim, I can start with what I'm claiming is the function whose derivative is 5x to the fourth and taking its derivative. And yeah, if I apply the power rule of differentiation to this, I get 5x to the fourth. And so that checks. So anytime you think you've thought backwards correctly, you can always check that by going back and differentiating either in your head or write it out. Okay, let's go ahead and look at the next page. So let's see, here's our next page. And we said that if f prime is 5x to the fourth, then f of x is x to the fifth. We're actually going to kind of improve this answer in just a few minutes, but hold off on that. Because we're thinking backwards, the way that you do on the Jeopardy show, we say that x to the fifth is an antiderivative of 5x to the fourth. And I think I even used this term on the last page. So when we do this process of going backwards, finding the function whose derivative is 5x to the fourth, we say that function that we found is an antiderivative of 5x to the fourth. Just like matter and antimatter are opposites of each other, differentiation and anti-differentiation are processes that sort of do the opposite. They are inverse processes, and we'll talk more about that a little bit later also. So in parentheses, I'm just going to remind you, it, meaning x to the fifth, is the function you must differentiate to end up with 5x to the fourth. You're going backwards and figuring out the function you have to differentiate in order to end up with some given function. So here's a little bit more formal definition. A function capital F of x is called an antiderivative of a function little f of x on an interval I if, and let's see if we can fill this in. Let's see, capital F is supposed to be the antiderivative of little f. So remember what that means is that capital F is the function whose derivative is little f. So if I did capital F prime of x, what should I end up with? I should end up with little f of x. So capital F of x prime is equal to little f of x for all x in our interval. And that's all we mean by an antiderivative. We found a function, capital F, whose derivative is whatever the given function is, little f. In our case up here, the little f of x was the 5x to the fourth, and we went backwards and found the capital F of x, whose derivative was 5x to the fourth. Okay, well, let's go ahead and see if we can just find the antiderivative of a few different samples, and we will also try to check each of those. And remember, you can always check your answer by going back and differentiating. So let's see what examples we have here. Here I'm told f prime of x is equal to 2x, and I'm supposed to go backwards and think, well, what would f of x have to be? So you're thinking, what would I have to have here so that when I differentiate, I would end up getting an answer of 2x? And what do I have to start with? I could start with the function x squared, and yeah, let's see, I can check that fairly easily. I'm going to actually move this slide just a little bit to the right to give me a little bit of room here to check. If I want to check it, I can go back and find the derivative of what I think is the correct antiderivative. I find the derivative of x squared, and what do I get? Sure enough, I get 2x. So x squared is an antiderivative of 2x. Well, why don't you take a moment, pause the video, and see if you can find the antiderivatives of each of these functions, and then go ahead and check your answer by differentiating it each time. Put a line here. This is our check over on this column. And just make sure that your answer is correct by differentiating. If you get the wrong answer when you differentiate, go back and try to figure out the correct antiderivative. And then we'll go through it together. Okay, let's try this together. Capital F prime is equal to cosine x. I have to think backwards and think, what function do I have to start with so that when I take the derivative, I end up with cosine x? And hopefully you got this one. Yeah, if I start with sine x, when I take its derivative, I do get cosine x. And you can even write it out. Yeah, when I take the derivative, do d by dx of sine of x, I do indeed get cosine x. And I put a little check mark there again just to say, yeah, this matches the derivative that I was supposed to find the antiderivative of. Okay, when f prime is 3x squared plus 5, again, you're thinking backwards, which is always a little bit trickier. So let's see if we can do that. Let me give myself a little bit more room here. The function that I would have to start with so that the derivative would be 3x squared, what would that be? That would be x to the third power. And because we can differentiate term by term, hopefully we can find the antiderivative term by term. Let's try it. What do I have to start with so that when I take the derivative here, I end up with 5 as an answer? I would have to start with 5x. And when I take the derivative of 5x, I do get 5. Now, just to double check, let me put a little green line here. Just to double check this, let's actually go through and formally take the derivative. You could do this in your head if you want to, but I'm claiming that the derivative of x cubed plus 5x is supposed to be equal to this thing, and that looks right. Derivative of x cubed, I'll just do it on the next line here, is 3x squared, and the derivative of 5x is equal to 5. So that checks with the function we were originally given. How about f prime equals e to the x? What function do I need here so that when I differentiate, I get e to the x? Well, e to the x is a special function. It's its own derivative. So if I start with e to the x and take the derivative, I get e to the x. E to the x is a very interesting function because it's a function that is its own derivative. When I take the derivative of e to the x, I get e to the x. But we've just discovered that it's also its own antiderivative. When I find the antiderivative of e to the x, I get e to the x. And again, you could check that just by differentiating, and we can see that if I do the derivative of e to the x, I get e to the x. So I think that one will check out fine. What about this one? F prime is secant squared x, and we're trying to think, what's f? What do I have to start with so that when I differentiate, I get secant squared x? Well, you have to remember your derivatives of your trig functions, but the derivative of tangent x is secant squared x. And again, if you want to, you could write that out formally, but we can see that if I take the derivative of tangent x, I will get secant squared x. This one's an interesting one. F prime is 1 over x. I'm asking you to think backwards and think, what function do I have to start with here so that when I take its derivative, I get 1 over x? And you have to recognize this as the derivative of a rather special function. Remember, we said that you can start with ln x and its derivative will be 1 over x. In fact, we even proved that you can start with ln of the absolute value of x, which is a little bit more a proper way of saying what the antiderivative of 1 over x is. This holds for a much larger set of x values. If you look at just ln x, remember that you can't put a negative into the natural log function. It's undefined there. So if you throw absolute values around your x, you've essentially doubled the number of values that your function is defined for, because now whether x is positive or negative, when you take the absolute value, you get something that's positive, and so ln of absolute value of x will be defined for all x except 0. Remember, you can't put 0 into the natural log function. So when we say what's the antiderivative of 1 over x, we like to write the answer as ln of absolute value of x, and then you've written a function that's defined for the maximum possible number of x values. In fact, it's defined for all x except 0. Okay, let's go ahead and look at the next page, and we are going to learn again about this concept, just sort of reinforce this concept of thinking backwards. We're going to play this Jeopardy game again, but now we're going to play it with derivatives. So here's the answer that the game show gives you, and this is you're the contestant, and you're supposed to come up with the question. So the category is, I've actually never seen this category on Jeopardy because they always have very easy science and math questions, but it says its derivative is, so that's the category that we're in. And let's just play the game. Its derivative is 2x. We've actually already done this problem. What would the question be? And the question is, you're really asked to find the antiderivative, the function whose derivative is 2x. And you already answered that on the previous page. That function would be x squared. So the question is really, what is? If you want to, you can add the words what is into here, x squared. Since Jeopardy contestants are always supposed to form their responses as a question. You did this one too. The derivative is cosine x. Then your question would be, what is sine x? And the derivative is secant squared x. Your question would be, what is tangent x? So exactly what we did on the last page, but formed in the context of the Jeopardy game show. Okay, well, let's think about this question. We said x to the 5th is an antiderivative of 5x to the 4th. But I want to ask the question, is there any other antiderivative of 5x to the 4th? So we said essentially that if f prime of x is 5x to the 4th, then capital F of x must be x to the 5th. And I want to ask, is that really true, or could someone come up with a different function whose derivative would still be 5x to the 4th? Well, I claim that, yeah, I could actually add something onto this. I gotta have the x to the 5th, because it's the only way when I take the derivative I'm going to get a 5x to the 4th. But can you think about what I could add onto here that when I take its derivative would drop out, so that I would still get a derivative that's 5x to the 4th? And yeah, you've probably thought of it. I could add a constant on. For example, maybe I would add 7, something like that. Well, I'm claiming this is an antiderivative of this. I can always check that claim by going back and differentiating. So let's just check it. X to the 5th plus 7, and I'm going to take the derivative of that. Derivative of x to the 5th, well, that's certainly 5x to the 4th. And the derivative of 7, which is a constant, is just 0. And so you notice that I do get 5x to the 4th. And that means that this x to the 5th plus 7 is also an antiderivative of 5x to the 4th. Could I add a different number on? Sure. I could add on something like x to the 5th plus 1,000. If I go back and take the derivative of that, derivative of x to the 5th plus 1,000, it will work out correctly, because derivative of x to the 5th will be the 5x to the 4th, and derivative of 1,000 will still be 0 because it's a constant. And so I'll still get what I want, 5x to the 4th. In fact, I could go ahead and say, gee, I could add any constant on. So I could do x to the 5th plus any constant, and we usually use a capital C there as the any constant. And when I take the derivative of this, it will still work out. So when I take the derivative, let's just double check, of x to the fifth plus any constant, I take the derivative of x to the fifth, that's 5x to the fourth. Take the derivative of the constant, that's 0. And so I do get 5x to the fourth. So I can really add on any constant here. So c could be any real number. So I'm just going to jot down here that this c could be any real number. It could be 1,000, it could be negative 1,200, it could be any real number at all. And when I take the derivative, that constant is just going to drop out. Now, there's another little question here. Are we sure that there are no other antiderivatives? I said that, yeah, I could have anything of this form, x to the fifth plus c, but could I add something other than a constant on? Well, hopefully in your mind you can at least intuitively see that probably I can't add anything other than a constant. If I added on anything with an x in it, I'll say anything containing an x, and x, then I'd sort of be in trouble. Like if I tried x to the fifth plus x, for example. When I take the derivative of that second term that involves something that isn't just a constant, it's not going to drop out and give me 0 as it did with my constant. So I think the answer is no, but I'm going to put a little question mark there because we haven't really proved that. We've just said, well, it looks like this is the best that I can do if I want to write down the set of all possible antiderivatives of 5x to the fourth. They would have to be of this form, x to the fifth plus a constant, and I couldn't add anything that's not constant onto this function. It looks that way, but we haven't really proved it. Let's go ahead and see how we would try to prove that statement by looking at the next page. And it turns out not to be that difficult to show. Let's suppose that capital F is an antiderivative of 5x to the fourth. In other words, when I take the derivative of f, I get 5x to the fourth. And now let's let g, capital G, be any other antiderivative of 5x to the fourth. In other words, when I take the derivative of this other antiderivative, g prime would also give me the same derivative, 5x to the fourth. So both of these functions, f and g, are antiderivatives of 5x to the fourth. Well, if you go back to an earlier section in our textbook, it's section 4.2, we said something about f and g if their derivatives are the same for all x values in some interval. We said that if capital F prime equals capital G prime, it means that capital F of x and capital G of x differ by a constant. And if you don't remember offhand why that would be true, you can think about a little graph. Let me get another piece of paper so that I can graph it for you. So I'll bring this page right back, but just to remind you of why that's true, what we are really saying is that capital F prime of x and capital G prime of x are the same thing. They're both equal to 5x to the fourth in this case. Well, what does that mean about the graphs of capital F and capital G? Well, it means that at each x value, the slope of the tangent line is the same for both graphs. So the slope of the tangent line to F, to that graph, has to be equal to the slope of the tangent line to G at each x. And that's because the derivative of the function is the slope of the tangent line to that function at that particular x value. So whatever our curves look like, if our curve G maybe looks something like this, and our curve F looks something like this, What we are saying is that when you pick a particular x value, suppose I pick this x value right here, we're saying that the slope of the tangent line to f is exactly the same as the slope of the tangent line to g at that particular x value. And what does that mean? It means the curves are what are called a parallel set of curves. They have to curve in exactly the same way. At each value of x that you choose, if I were to choose a different value of x, such as this one, at each value of x you choose, the slopes of the tangent lines, tangent line should look more like this, to these two graphs have to be exactly the same. And so they bend in exactly the same way. And what do you notice about two graphs like this that are kind of parallel and bend in exactly the same way all the way for all x values in some interval? Well, the distance between those two functions, the vertical distance, the difference in their output values, is exactly the same. So this distance between the purple and the green graph is equal to this distance between the purple and the green graph. And so the two functions differ, we say, by some constant, which we are calling capital C. The vertical distance between the two curves at every point is a constant value. So that's what we said back in 4.2, and I'm going to just go ahead and use that information now. If f prime and g prime are the same, then f and g differ by a constant that we call capital C. All right, so let's go ahead and fill this in. Thus, if I were to subtract g of x minus f of x, I would get that constant. They differ by a constant means their difference equals some constant. And what I'd like us to do now is just to solve for g in this equation. I'm going to move the capital F over. G of x would be capital F of x plus that constant. And so we can go ahead and say, in this case, capital F of x was, for this particular antiderivative, capital F that we found originally was x to the fifth. So for our particular example, we would get that any other antiderivative must be of the form x to the fifth plus c. And so this expression that we have right here, and maybe I should say where c is any real number, c is any real number. So this is the most, we say it's the most general form of the set of antiderivatives, or sometimes we're just a little bit sloppier and we say it's the most general antiderivative of 5x to the fourth. In other words, I'm going to put i.e. it's the set of all antiderivatives of 5x to the fourth. There aren't any other of some other form other than x to the fifth plus some number. So we found the set of all antiderivatives of 5x to the fourth, and the x to the fifth that we originally found is really just one out of an infinite number of antiderivatives, but they all have this form. They're all of the form x to the fifth plus some constant, and the one that we originally found, the constant was just equal to 0. Okay, what I want us to do next is this example where we're asked to find the most general antiderivative, in other words, the set of all possible antiderivatives of the given function. So suppose we're given little f of x is 10x to the ninth, and again by little f we mean exactly the same thing as capital F prime of x. So we're saying that the derivative is 10x to the ninth, and we want to find the antiderivative of 10x to the ninth. So what would capital F of x have to look like? Well, in order to get a derivative that has an x to the ninth power, I would need an x to the 10th power. And will that work? When I take the derivative of x to the 10th, I would get 10x to the 9 by the power rule for derivatives. But in this case, I'm asked to find the set of all possible antiderivatives. So I could add on any number. I could add on 7, I could add on 1,000, I could add on any constant. And so we just write down plus c, where we assume that when the person writes the plus c, that c can be any real number, or you can write it out specifically the way that we did up here. But in these problems, we do so many of them that it's implied that c can range over any possible real number from minus infinity to infinity. Let's try part B. I have f of x equals 2x, and so again you have to think backwards. We said that if you start with x squared, when I take its derivative, I will get 2x. We did that problem before. But now I want the set of all possible antiderivatives of 2x. And so I should write a plus c on here. And if I'm not sure, remember you can go back and just take the derivative. So you can say, oh, okay, I'll just take the derivative of what I'm claiming is the correct antiderivative, and I would get 2x for the derivative of x squared, and derivative of c is just 0. So I do get 2x, and that checks with the function that I was originally given. So you can always check your answer, even if you can't find the correct answer to one of these thinking backwards problems, you'll at least know that you found the wrong answer. Okay, let's go ahead and look at the next page. On this page, we're going to learn some new terminology. It gets a little awkward to say the set of all antiderivatives of a function. It's awkward for a teacher to ask the question, you know, here's a function 2x, find the set of all antiderivatives of 2x. It's just very long and awkward. And it's awkward also notationally because we don't really have a notation yet for finding the set of all antiderivatives. So that's what we're going to talk about next, and it has to do with defining what we call the indefinite integral of a function. So I want to remind you, this is just a little remark, that we had what was called an operator notation for derivatives. We've used it many, many times. Remember how the operator notation looks? It's a d over a dx, this looks like a little fraction, and then usually we have square brackets and there's some function inside here. And remember what this operator outside means. It means to do a certain process. It's sort of like a square root symbol says take the square root of 25, and then you say, oh, that's equal to 5. This means find the derivative of whatever function I plug in here. So let's go ahead and I'll try to write this out fairly nicely, and let me write it out the way I have it in my notes. So this means find the derivative of whatever's inside the square brackets. I'll just say of what's inside these square brackets. So we've done this a million times, but the derivative of sine x, so this operator notation says find the derivative of whatever's inside the square brackets. Find the derivative of sine x, we get cosine x. If we're asked to find the derivative of x to the 10th, we say, oh, that's easy. Okay, I'll use the power rule for derivatives. That would be 10x to the 9th. Well, there's a similar notation for finding antiderivatives, and it's a weird kind of notation. It'll look kind of crazy to you, but I promise that later in section 5.1/5.2 we will talk about where these symbols came from, and they will make some sense, and you'll understand why we have this kind of strange symbol. Just like the operator notation for finding derivatives looked really weird at first, the same is true for finding antiderivatives. So there's a symbol for finding antiderivatives, and we have this long kind of curly, it's like a vertical line, but it's curly. Most people think of it as a stretched out S, and we'll talk about why it's a stretched out S in 5.1. And then there are square brackets, and then there's a dx at the end. So these two portions, this long stretched out S and the dx, are all part of the operator notation. So it looks a little weird because usually we're used to having an operator notation that there's just a single symbol and then the square brackets. But both of these are part of a single symbol that means find the set of all antiderivatives of whatever's inside the square brackets. So this symbol means find the set of and it really is all antiderivatives. Antiderivatives of whatever's inside the square brackets, of what's inside these square brackets. So just like this means find the derivative of whatever's inside the square brackets, this sort of two-piece symbol means find the set of all antiderivatives of whatever's inside the square brackets. So for example, if I say, put this symbol here, we'll talk about how you read this symbol on the next page, but if I put this symbol here, this operator symbol, it means find the set of all antiderivatives of 5x to the fourth. We already did that problem, and we said that that's x to the fifth plus any constant, and that's the set of all possible antiderivatives of 5x to the fourth. So it's a nice operator symbol that tells the person looking at it, oh, I know what I'm supposed to do with 5x to the fourth. This symbol, I think of it as a single symbol, says find the set of all antiderivatives of whatever's inside the square brackets. Well, let's go ahead and look at the next page, and we'll talk about how we say this symbol in words. Here we know we just say find the derivative of, but we have kind of a shortcut vocabulary for this symbol so that we don't have to say all of this. You notice it takes a long time to write find the set of all antiderivatives of what's inside. It's just too long to say, and so we come up with a new way of saying it and some new vocabulary, and let's go ahead and see if we can talk about that. So it's a little bit of new terminology. This stretched out S symbol is called an integral sign, or more properly it's called an indefinite integral sign. Oftentimes we're sloppy and we just say it's an integral sign. And we'll learn about, well, what does that mean, indefinite integral? That sounds really weird, but we'll learn about this word indefinite and why these are called indefinite integrals later. I believe that will be in section 5.3, I think, is where we'll learn about what are called definite integrals and the difference between an indefinite and a definite. What we are talking about right now are called indefinite integrals, and oftentimes we're sloppy and we just say this is an integral sign. So when I put this symbol together and write the integral sign and the dx, the operator notation that says find the set of all antiderivatives of whatever's inside. Oh, and notice here I didn't put the square brackets around the 5x to the fourth as I did on the previous page. And oftentimes if there's only one term in the function we're finding the antiderivatives of, we don't put the square brackets. But this would just be read the integral, and really technically it should be the indefinite integral, but in practice we almost never say that. The integral of 5x to the fourth. And sometimes we actually say the words dx at the end, so sometimes you'll hear this read the integral of 5x to the fourth dx, and that's fine to include the dx as you say it. Sometimes we'll leave that off and we're a little bit sloppy. Let's look at this statement and just write down how it's read. It's a complete statement where I have the integral of 5x to the fourth on the left, so I'd say the integral, really meaning the indefinite integral of 5x to the fourth, and again you can say the integral of 5x to the fourth dx, that's a little more proper, equals or is x to the fifth plus c. So notice that this statement, the integral of, is really the same, put a different color here, the integral of 5x to the fourth is another way of saying the set of all antiderivatives of 5x to the fourth. And you can see this is just so much longer to write, but this left-hand side of the statement would be the same thing as saying the set of all antiderivatives of 5x to the fourth is x to the fifth plus c. And it's just so awkward that we come up with this new word, integral, to mean the set of all antiderivatives. look at this little bullet point here. It says finding the answer to the problem integral of 5x to the 4th dx is called integrating. Some little quotes there, 5x to the 4th. So when we go through this process of finding the set of all antiderivatives and saying, oh, that's x to the 5th plus c, we say that we have integrated 5x to the 4th. We've found the set of all antiderivatives of 5x to the 4th. Well, let's go ahead and see if we can do some examples just to get used to this notation. These are actually functions that we've already found the set of all antiderivatives for, but if I write find the following integrals, find the integral of 10x to the 9th dx. Well, that means I'm asking you to find the set of all antiderivatives of whatever's inside. And you notice I didn't put the square brackets there. You can imagine them in there if you want to. But 10x to the 9th is a function I want to find the set of all antiderivatives of. And let's see. To get 10x to the 9th when we differentiate, I need to start with x to the 10th. Derivative of that is 10x to the 9th, and I can always add on any constant. By the way, this constant that we add on is called the constant of integration, or sometimes we simply say the integration constant. So that's what we call C. Now that we've introduced the word integral, C is called the constant of integration or the integration constant. Why don't you try this one, maybe pause the tape for a moment and just write out the answer. Okay, let's try this one together. It's the integral of 2x dx. That really means find the set of all antiderivatives of 2x. And what would that be? I'd have to start with x squared if I hope its derivative to come out to be 2x, and then I would add on my integration constant. And c again can be any real number. By the way, for both of these, if you're not sure that you've done the problem correctly, and perhaps for ones that are more complicated, how do you check that you've come up with the right answer? How do I check that this answer is correct? Remember, you can always check an integration problem, an anti-differentiation problem, by going back and differentiating. So one of the wonderful things about doing integrals or antiderivatives, finding the set of all antiderivatives, is that you can always make sure that your answer is right. You can always go back and differentiate. So if I differentiate x to the 10th plus c, oh yeah, derivative of x to the 10th is 10x to the 9th. Derivative of any constant is 0. And so I get 10x to the 9th. And notice that this matches with what we were originally asked to integrate. So we get a match. I put a check mark here because this matches the original function that we were asked to integrate. Same thing down here. You might pause the video and just check your answer of x squared plus c and show how you would prove that that is the correct answer. Then we'll do it together. Okay, well, let's try checking this together then. All I do is take my answer and differentiate it. So I say, well, what is the derivative of x squared plus c? Derivative of x squared, oh yeah, that checks, that's 2x. And derivative of c, the derivative of any constant is 0, and so I get 2x. And I notice, yay, that matches the function that I was originally asked to integrate. It's the same function that I was originally asked to integrate, and so I know that I've found the correct antiderivative. Remember though that the set of antiderivatives is the answer to the problem, and the stuff that we did in green is really just the check. All we did was go back and check that those answers were correct. Okay, let's go ahead and look at the next page. So here we have some more integrals to do, and let's go ahead and just go through these. These are all ones that you've looked at before in terms of finding the set of antiderivatives, but now we're using this new integral notation. So integral of cosine x dx, we just go ahead and find the set of all antiderivatives of cosine x, whatever is trapped between the integral sign and the dx. And so that would be sine x, but of course we could add on any constant. And as usual, I can go back and check my answer either in my head, or I can go through and check it carefully. And if it's a more complicated function, you'll probably want to write it out rather than just checking it in your head. But if I take the derivative of sine x plus c, the thing that I am saying is the answer, the set of all antiderivatives of cosine x, I can check it by just going back and differentiating. Derivative of sine is cosine x, and derivative of the constant is 0, and I do get cosine x. So great, that checks because it matches the function I was originally asked to integrate. Okay, I'd like you to stop the video and just write out the answers to these last three, and if you want to, you can go through and do the check either writing it out or do it in your head, and then we'll go through them together and go on to something new. Okay, let's go ahead and look at these. You've actually been asked to do all of these, but not with this new notation. Integral of e to the x dx just means find the set of all antiderivatives of e to the x. Well, e to the x is its own derivative, and it is its own antiderivative. Derivative of e to the x is e to the x. So e to the x is an antiderivative of itself. But if I want the set of all antiderivatives, I just add on my integration constant c. And don't forget that we're really writing down here a set of answers. It's actually an infinite set of answers, and that's because our integration constant c can be any real number. So you're really writing down in this one succinct way the function e to the x plus 0, that's just e to the x, that's one of our antiderivatives. But you're also saying things like e to the x plus 3 is an antiderivative. E to the x minus 100,000 is another antiderivative. E to the x plus square root of 2 is another antiderivative. You're really saying an infinite number of antiderivatives as c runs over every possible real number from minus infinity to infinity. This one, the integral of secant squared x would be tangent x plus c. And again, that's because the derivative of tangent x is equal to secant squared x. This one, integral of 1 over x dx, well, I want to write it down in the most, I guess the answer that is valid for the most x values possible. So instead of just writing natural log of x, what should I write there? I'm going to write the natural log of absolute value of x, and then I'll add on my integration constant c. And again, that's just so that this function is defined for the biggest possible set of x values. And in an earlier section in the class, we went ahead and showed that the derivative of ln of absolute value of x is equal to 1 over x, whether x is positive or negative.